Okay, so it's great to see people again. I'm sure a few more may come in yet. We are continuing our review of some key features of Scala with a particular focus on Scala applied to data science as befits its title, a scalable language. That's what Scala means. Okay, and we're going to be focusing on, we have focused in last session on a key feature of Scala in taking advantage of its functional features, and that is the use of higher order functions. Last time we saw map, reduce, filter, and we talked a little bit about fold as well. And we saw that how we could create pipelines within Scala to process sets of data. I hinted at the fact that these pipelines could support some efficiencies for us. This time we're going to expand on some of that knowledge. We will also be expanding our knowledge of defining methods and functions in Scala. Take a look in particular at polymorphism, a topic about which Anahita inquired in the previous session. We're also going to take a look at the broad topic of laziness, okay, non-strictness, how Scala allows us to define computations where we define the computation on one hand as something separate from its actual the calculations taking place. So we define it up front, and then we trigger the computations at a later time, often on an as-needed basis. Okay? So we're going to be looking at laziness with a particular eye towards how laziness, ladies and gentlemen, aids scalable processing of large amounts of data. Laziness will play a key role by allowing us to avoid the memory demands associated with typical data processing. There's plenty of room in the corner, Kurt.
Yeah, I don't know if I can carry. I'm not going to carry my chair across the room.
Yeah, but you could shift around. Everyone could shift. Yeah. Okay. Richard. Okay. Okay, left shift. Okay.
Clean cup, move down.
Okay. Great. Okay. Welcome. I appreciate that. Richard Feynman has a famous paper called "There's Plenty of Room at the Bottom." I don't know if you've ever seen. Okay. Okay. So we talked about a number of features of Scala. I'm not labor at this time. But we're focusing on the components that are most applicable to data science. So last time we took a look, skipping through a number of things here, about which we'll be coming back. We took a look at Scala methods and functions, and we saw how we could define these on the Scala command line, and we interactively built up a little function and saw how we could use something called currying to in fact write a function that's evaluated in two different pieces. So we saw we could define anonymous functions that have no name, and we saw that we could define a curried function which takes one argument, which itself returns a function, which takes another argument and returns a value. Do you remember that? This currying. I'd like to expand on some of these features, highlighting some features we didn't have time to touch on last time because we were in too big a hurry, okay? And the first of the features is Anahita asked a question, a prescient question, a question about types and defining a function. So we had a function last time define something like foo, right? And it took a value that was an integer. I would invite you to follow along, even though we've seen this before. And this value might be, the square of of v. So it takes an integer as an argument and returns an integer that's the square of what's given to it, right? And Anahita asked a question, which proves prescient because it's going to be an important component of our understanding in coming weeks. Does foo have to operate on particular types here? And I said, well, no, this is somewhat of a more advanced topic we'll be coming to. Now, ladies and gentlemen, it's the time to come there. Suppose we wanted foo to not only accept integers, we want it to be able to accept other types of things as well. Okay, particular application of it, perhaps to a double, would accept a double. A particular application to an integer would process an integer. Okay. We're going to define such a function now. We'll see how we can define something like that in its most basic form. So let's define a function called myIdentity. Okay, this is going to take in an argument of whatever type, and it's going to return that argument back. Okay, let's start simple. Okay, Winchell has a certain fondness for the identity method. Okay, so this takes in right now an integer. But we're going to imagine it takes in something different. It's going to take in something of type t, okay? Of any type t. This could be an integer, it could be a double, it could be a string, it could be any number of different things. And instead of squaring it, it's just going to return it. Now, we could give this to it. It would be very unhappy because it won't know where this t comes from. It won't know what t is. So we have to tell it, okay, this function is type parameterized, meaning it carries with it what's called a type parameter that specifies this type of t. In other words, it's when being applied to a certain type, this is how called t. This is how it's defined. Okay? Yes, Scott.
So, in other words, when we pass something into this function, it reads the type of it as well as the value.
It figures out the type. That's right.
And then I'm assuming you use something like matches to do different things on different.
That's right.
types.
Yeah. Yeah. So you could say, okay, so you see that we've defined a function and a method, and this method has some parameterization. It says it's parameterized by type t, meaning there's different versions of it for different types. Okay. It to do its job, it needs to not only know the value passed to it, it needs to know on what type that value is defined. Okay. So I could define, my identity of 1, or return a 1. I could define my identity of food, or return a foo. I could define my identity of 3.14159, and it will return back that. Okay. So here we have a function which can operate on multiple types. We've defined in a single line a function that can operate on a huge variety of types. Okay. Which has some benefits. Now that's a rather artificial function. Let's do one that's a little bit more interesting than that, if we could. Okay? Yes, Kurt.
Are there type classes like numerical types?
Indeed.
Wait, we can make a class of types?
Well,
there's
you
could define a function
whole super types of types.
That would do like multiplication, which
Correct.
makes sense for numerical types, but not for
Correct.
string.
So we could specify using type bounds, which is more advanced than I want to get into in this little section of the lecture. You could specify that t needs to satisfy these given properties, including to the level of saying it needs to have a foo function, a function called such and such. But you could say it needs to be a numeric type, or you could say it needs to be a collection, or you could say it needs to be a.
So it needs to inherit from something from a certain class.
That's right. Yeah.
Or that means it is a certain class.
Yeah.
Interesting.
So
we could also use those as conditions in match statements.
Yes. I mean, you could. So I'd have to unpack what that means to more fully explicate it, but
you can do it.
yeah. Okay, so let's create, my list. Okay, my list of tuples. Okay. And this is going to take two components. 1 is it's going to take a value, 2 is it's going to take a value, 3 is it's going to take a value, 4 is it's going to take a value, 5 is it's going to take a value, 6 is it's going to take a value, 7 is it's going to take a value, 8 is it's going to take a value, 9 is it's going to take a value, 10 is it's going to take a value, 11 is it's going to take a value, 12 is it's going to take a value, 13 is it's going to take a value, 14 is it's going to take a value, 15 is it's going to take a value, 16 is it's going to take a value, 17 is it's going to take a value, 18 is it's going to take a value, 19 is it's going to take a value, 20 is it's going to take a value, 21 is it's going to take a value, 22 is it's going to take a value, 23 is it's going to take a value, 24 is it's going to take a value, 25 is it's going to take a value, 26 is it's going to take a value, 27 is it's going to take a value, 28 is it's going to take a value, 29 is it's going to take a value, 30 is it's going to take a value, 31 is it's going to take a value, 32 is it's going to take Okay, it's going to be parameterized by type t, meaning there's going to be versions of it for different types. It's going to take a value of type t, and it's going to take something n, which is an integer. And this is going to be the count of elements in that. Okay. And what we're going to create here, ladies and gentlemen, is a list of tuples, each composed of pairs of t. So this is going to be called a tuple 2. Okay, that's the type of a tuple. It's going to be a type t and t, so it's going to be a pair, like 1, 1, 3.14159, 2.0. They're going to be a pair of things of the same type. Okay. This is going to be the type of the thing returned, and I lost it. Okay. Okay, that's most unfortunate. Okay, my list of tuples. Okay, here we'll go through this again. Okay, and this is going to be equal to a list of 2 tuples. In other words, it's a tuple can be of length 1, 2, 3, 4, 5. This is going to be a length of 2. Each element is going to be of type t. So there's 2 of them here. So it's going to be the first and the second. And then, ladies and gentlemen, we're going to say fill of n. In other words, we'll have n of them, and each of them is going to be v comma v. Okay. Probably somewhere in there I've made a mistake. So, okay, if you want to treat it as a partially defined function, okay. So why is it not happy with that? Okay. So I would have thought that should work just fine. Let me take a peek at something I did earlier. Okay, list of tuples. Okay. I was doing something a little bit different here. Okay, and we are going to use it to, got it. Okay, yeah, of course. So what we're going to do here is, what's that? I think actually what we can just do is this. Okay, sweet. Okay, that's all we need to do. All right. So here, ladies and gentlemen, is something which I could give it my list of tuples, okay? And we'll come back and explain this in just a second. My list of tuples, and I'm going to give it a certain value, 3.14159, and I will give it 3 here. And what do you think is going to be returned? Well, it's going to be a list of 3 pairs. Why pairs? Because this is how in Scala we denote a pair. We say, it could be 3 and foo. That's a pair of a integer and a string. So when we write something in parentheses like that, we're denoting a tuple. In this case, it's a pair. Okay. This thing here, this function, it's a type-parameterized function. I give it 2 things here. One is the value to put into the list, and this is the number of pairs to put in that list, and it will return for me a list of the appropriate type with n elements in it, in this case 3, 1, 2, 3. Each of those elements has the value, is a pair of whatever value was given here with itself. Okay, so this is an example of something that's a little bit more sophisticated. I could create something of size 2, and here's a list of just 2 such pairs versus here, which is a list of 10 of them. Yeah.
Can we have multiple parameterized types?
In other words, could we have S and T?
Yeah.
Absolutely.
So we could create something that takes in 2 type parameters,
yes,
2 variables and int, and then creates copies of.
Yeah, let's try to do that. No guarantees, but let's do it right now. Okay. My list of, I'll call it my list of pairs. Okay. We'll take an S and T. We're going to specify V of type T, U of type S. Well, n of them, and and it's going to fill out a list of pairs where instead of just being V and V, it'll be U and V. What do you think about that? Good or not? Do you see what I'm doing? So now we're going to have my list of pairs. I'm going to be able to give it two arguments of different sorts and a count, and it's going to create for me a list of pairs of U and V that are of these respective values. So let's go try it. So I just entered it, and here we go. I'm going to say the values I want to put in there are, 3.14159. You notice I like that number, and for good reason, because it is a fairly good approximation to pi. Okay. Sorry? I forgot n. Yes, thank you. I'll have 3 of them up front. Sorry. I fed def. I don't want def. Oh, man. Thank you. I left my def. Okay. Okay, there we go. Let's just created 3 pairs of these in an appropriate list of doubles and strings. Okay? So this is an example of a type-parameterized function. Type-parameterized in the sense that to do its job, not only does it need to know about each of these values given to it, but it needs to know the types of them. And how does it figure out those types? It figures them out from looking at these arguments and saying, okay, you have a double here and you have a string here. So S must be double, T must be a string, and then you have this int, which is the count of them. Okay?
Can we define 2 parameters to put in that field of n and m? Or that's just
Say that again?
Can we use 2 parameters for field? Field n and m.
You mean for this thing?
Yeah.
Not for fill, but there's a 2-dimensional analog to it for an array. If that's what you're thinking of, if you're thinking about like a grid, you want to be able to fill up a grid. Yeah, there's something comparable. It's not directly fill though. Okay. Actually, so maybe named fill. Actually, excuse me. Sorry, Winchell. But
you can just complex fill with info.
Yeah, but no, there's actually a 2D version of it, though. And I can't remember off the top of my head if it is, in fact, called fill or something different, but it will do the same basic job. And these functions here you'll notice they're functions not of a particular list, but of lists. So we ask list, hey, fill up, a list, an initial list, with this many elements, each of which is given by this pair. Now, there'll be something you may notice here. We'll come back to that. One thing is this issue that fill looks like a kind of curious thing. It takes n here, and then it has a separate list of parameters here. Do you see that? Mm-hmm. This is what's called, ladies and gentlemen, a curried function. Well, we curried our own function last time. Although I'm sure that this isn't quite as good as the curries to which Tina is used in Kerala. It was a good curry nonetheless, which was this one here. So this function, remember, took in a first argument, and then it returned a function which took in a second argument, and then gave the sum of them. Do you remember that? This function from last time? Ladies and gentlemen, we can actually define this more easily in Scala. And I'd like to see how that's done. Yes?
So that list.fill actually first returns a function that now takes the
Yes. Correct.
Really interesting.
Yeah. I share your sentiment. Yeah. Okay, so here's this fn increment by function generator. We're going to say my curried function. Okay, my curried add. How do you like that? Okay. So what this is going to take in is and just by analogy with this one, we'll call it C and N. Okay. Here we go. We'll take in a C first. And we could make this specific to int, but then maybe we'll do that up front, and then we'll come back and make, We can make it specific to int for now. We could come back and change that. Okay, make it for numeric types. Okay, so here's C, and then here's n. This takes in n, and it equals what?
C plus n.
C plus n. There's my curried add, right? And what if I were to just apply this to a value, right? What do you think I get back?
Pointer.
In function.
Okay,
Yeah.
it's not gonna allow that. I have to actually put the underbar after it. We talked about this last time. Remember the underbar indicating a partially applied function? We want this to be treated as a function. It's gonna be, if you just give it this, it's gonna be looking for the extra argument. In order to say, hey, look, give me back a function here. I want a function back. You know, I'm not going to give it the other argument now. We put this underbar after it, and this gives us back a function. What's the job in life of this function that it gives back? Can anyone tell? What do you think the job in life of this function that's returned by this particular call? It adds 2 to things. Yeah, exactly. So we could say, you know, val, you know, test fn equals this thing, right? And then we could do test fn to 5, and what will it give?
7.
Indeed, you're a quick study. Okay. So ladies and gentlemen, we've just seen, in terms of significance here, how we can define a curried function using multiple parameters, okay? And that's exactly what we saw above with this fill, right? We specified one parameter, and it gave back a function which expects, you know, an additional argument that it needs to fill in for each element, right? And there's some more subtlety to that thing that it takes, because it turns out it takes an expression that it will keep undervaluated until it applies it each time.
So if it changes in the meantime, it can actually give different values?
Yes, you could give successively larger values.
Interesting.
Okay. So here, ladies and gentlemen, here I'll.
Wait, I
have
didn't
a-
get
I have a
Yeah.
question about
Okay,
the
we're going to
list
come
fill.
back to that issue.
I have a question
one
about
step
the
at a
list fill.
time.
It can derive types to the point that it knows that u comma v is a tuple and not just a single value.
Yeah, because
That's really interesting.
you know, it looks at this and it says, oh, okay, you want a tuple. That's what the parentheses mean. Maybe for good measure, I'll, you know, put this in there. This is a 3 tuple. That's because it's in parentheses, it recognizes that. And then it says, oh, okay, that's an integer, that's a string, that's a double. So this is a 3 tuple there that it creates. Okay.
We might call it a threeple.
How about a triple?
A triple is a nice.
I think it's twople, threeple, fourple, fiveple.
The tuple doesn't come from the pair, does it?
Inflationary language?
Yeah.
Triple, young man.
Wrong crowd again.
Okay, so maybe I will hit this point a bit more because there's a question about it, and I'd like to be responsive to student questions. Ladies and gentlemen, we saw how we could define here a function, and we last time we saw it manually, how we could define it this way, right? It requires one argument, and it takes another argument, and it does something with both. Remember that? And I argued that this is important. One can actually engage in what's called staged computation. Staged not in the sense that it's fake by any means, but staged in the sense that it is staggered, it is phased. So we could take some of the values early on, do some computations on them, and then take the rest of the values later when they're available and do the rest of the computations, okay? This is a point of significance. But I want to take this in a slightly different direction now. Another feature of this is that this n plus c doesn't get evaluated until later. You give the first argument. N plus c is not going to be computed till you give what?
In C.
You give n later, right? It's being deferred. What do you think would happen if we, ladies and gentlemen, were to, instead of taking a particular value here, we actually took nothing. We actually didn't require something to be given. We actually just take nothing at all. We don't require anything in that first pass, but we require nothing. We do require nothing. Let's try this, okay? It's hard for me to fully express it in words. Let's try this. So we're going to create a well, we can define it just the way we did there. My curried add. So I'm going to say my deferred print. Okay. So here we go. This is going to take nothing as an argument. Okay. Later, it's going to take an int, and its job is going to be to print out that int. Is that okay? Okay. Watch this. Okay. Now wait a minute. Is this equal to that? Remember, I told you there were two types of methods we could define in Scala. One of them was returned a function. It computed a function and returned a value. What if the other one? Remember that? It's a procedure. Yeah, it's a subroutine. All it does is do something, and that's what this does. It doesn't actually return a value. Its job in life is to print something. Okay? Do you see that? Okay. Now watch this.
How do you call the rest of it?
Sorry?
How do you call the rest of it?
Okay, we'll see, Scott. We'll see. Okay, val. Okay, let's do val. Deferred print here equals my deferred print. This returns now a function, and what do I have to call this function with in order to get it to print it out? I need to call it with what? This is a function, right? Maybe I should have called it deferred print function. Why not? There we go. Now deferred print function, I'm going to apply it to 2, and what will it do? Yeah, it'll print out 2. Apply it to 3, it'll print out 3. The point is that we kind of deferred this part of the computation, okay? We deferred it. Let's do something more than that, though. Let's try this in a different way. Suppose I say value deferred print 2, function 2, and I'm going to say this is defined, and I'm going to use parentheses to indicate this. It takes nothing as a parameter, and it prints out hello. Okay? This is what it does. Okay, so this is a value, and what sort of value is it? It's a what?
Function.
It's a function, and it takes nothing, and it prints hello, right? Okay, great. Okay, so I could now say deferred print function 2, and I could call it, and it's going to say hello. How if I do it again? Each time it just says hello. All it's done is it's deferred this work, right? Until I call it with no argument, right? All it's done is it's deferred the work going on here until the point where it's called. Okay? Do we see that? Okay. And we saw with closures last time that we could actually take one argument first and then remember it and print it out. Okay.
So we could do something like events?
Yes, precisely. We can allow for handling of events at a later time by allowing these things to be sort of placed in data structures, so when they are called, they do some work for us. You know, when an event comes in, we will trigger this
So in effect,
this
if
function.
it's using logic and analog, all events that we write this way could be dynamic events.
Yeah, they'd be dynamically evaluated.
We could have all kinds of parameters associated with those events. Wow.
Okay, ladies and gentlemen, I'll take this one step further. So we've just deferred this computation, okay? I'd like to do something further here. to expand on this notion. I would like to define a deferred function 3 that will do the following. Okay, what this is going to do is it's going to take in as an argument an expression, and it's then going to use that expression at several places. So what's going to happen is we're going to have this, okay? It will take in some expression, and we will then use it at 2 different places. So here we're going to do it. This will be called call it value v, but we're going to write it this way, okay? This is going to be something that yields an integer, okay? That's right. And then we are going to return back something that's a list of fill with 3 items in it. Fill, yes, and then we're going to give v as the element. Okay, so we're going to deferred print function 3. It's actually not a print function right now, but that's fine. And we will say 2 plus 2. Okay, and it's going to give back to us 4 here. Okay. What this is indicating is that it's taking in this expression, and it's actually not going to evaluate it until we actually use it. Okay, I'd like to show this. I'd like to show this to you graphically how this occurs by doing the following. So I'd like to create a function. I'd like to create a function here that is going to, and I'm thinking the easiest way to do this, maybe for simplicity, we'll say print and return 2. Okay, print and return n. Okay, and this is going to take in an n. It's going to be an integer. It takes in. And its job in life is to do 2 things. First, it's going to print n out, and then it's going to return n. Okay? Oops, what am I doing? It's a function. What am I doing? I've got it, okay. So this is going to, this is a def. Sorry, I shouldn't have done it as that. Okay, fine. Def it. Okay, this is defined. This is going to be a function whose job in life is to do that. Print and return n. Now watch this. Oh my gosh, okay. I just died out of that. Okay. I pressed Control C. Sorry folks. I'm gonna have to go define this thing again. You already have it defined. I'm just gonna have to go back and paste this in. Okay, there we are. So we have this defined print function, and then I define this function here, print and return n, whose job in life is to return a value, but printing it out first, okay? And we are going to call now deferred print function 3 with print and return n, okay? And we'll do it for 4, okay? Okay, oh, not def. I just want to call it, thanks.
Oh, interesting.
Okay, and ladies and gentlemen, what do we see here? What does it return? Well, we know what it returns. It's a list of 3 elements, each of which is this value v. But what else, so it returns that, no surprises there. But what else does it And remember, print and return 4, what does it return? 4. So each of the elements of this is 4. But what else happens?
It printed them out first.
It printed them out first, ladies and gentlemen. So each time it is using this value, it is actually calling this function, okay, this function here. Each time it's seeking to use the value v, it's actually calling off the expression that I gave it. This is called a call by name parameter, this thing here, ladies and gentlemen. It's called a call by name parameter, meaning it's lazy. I give it an expression for it to compute, and then whenever it needs to know the value of v, it will reapply that expression right there.
With that expression currently being 4.
So let's be clear about what's happening. Suppose I were to apply this expression. What do I see? It prints out 4, and it gives back the value 4. Do you see that? Prints back 4, prints out the value 4, returns back 4, right? Here, ladies and gentlemen, here we filled a list of how many elements? 3 elements, each of whom was given by this value v. So for each time, each of these 3 elements, it asked, what is v? And guess what it did for each of those times? It called this function. Why did it call it? Because that's what I gave it for v. So you could think of this as passing in what's called a call by name semantics. It's passing in this formula or expression to be evaluated. It's passing in this computation to be evaluated on an as-needed basis. Every time it needs it, it evaluates this expression.
So instead of what normally you see in stuff like Java is that when you put that in there, it would first compute print and return 4 and then pass that to the other function.
Right.
This passes
Correct.
the function itself.
So let's make that distinction. It's a fine didactic point. And let's contrast that with what would have been happened if we did this, Scott. What would have happened if we had just said, it's a great Gedanken experiment.
What's that?
It's a thought experiment.
Oh, okay.
Okay, here we go. So this is just going to be called print function 3, okay? So this, in contrast, the one above, I had this, right? Which was a by name parameter. Suppose I didn't do that. I just called print function 3. What if I call that here print function 3 with this? What do I get?
You'll only get one.
Only get one time it calls because, ladies and gentlemen, it calls this, it computes the value v. It calls this, it gets back the value 4, and it prints out along the way, right? It prints out along the way, it gets back the value 4, right? Here we go. And this is where it printed out. Having determined that value of v, it then calls print function, which takes v, this value, 4, and fills a list of 3 elements, each of whom is v. This function up there, with the call by name semantics, does something kind of conceptually similar, except every time it needs v, it's evaluating it anew.
Meaning we can actually get it to print 3, 4, 5.
Yes, we could, and this is where I'm going. Watch this.
Oh boy.
Watch this. Okay? So now what I'm going to do, this is a very useful pattern in Scala. I'm going to say, I won't do it with an array, I'll do it with a list, okay? List.fill 10 values, each of whom, ladies and gentlemen, is going to be drawn from a random number, okay? Scala.util.random, capital .random, okay? .next int, okay? And that's going to give me back a set of successive random numbers. Or if you prefer to look at doubles between 0 and 1, this is what you'd do. Here I have filled a list with successive random numbers. Do you see that? Now, how is it that it didn't just evaluate this up front, pass that value to fill, and then fill it with the same number that many times?
The fill per, either next double is calls by name.
Yes, this argument for fill is called by name.
Or we could see that it filled the list with that function, then evaluated the function for each element of the
Exactly.
list.
That expression is being evaluated for this time, this time, this time, and each time it returns a different value. So when you ask, could we fill it with 3, 4, 5? Conceptually, that's the same idea here. We give it a function that has some state. Each time it changes something. In this case, it's getting a new random number and it's updating the random number seed each time, and so it's drawing separate random numbers. So Scala has the ability to do this. Now, suppose we didn't have call by name parameters. How would we do that, ladies and gentlemen? How would we do it if we didn't have call by name parameters? Well, it's very straightforward using something you know. We could actually, ladies and gentlemen, instead of passing in this, what we could pass in. So suppose this is, fill strict, or non-lazy, fill no call by name. Okay, just to belabor the point. Suppose it didn't give us this ability to give it something that. Suppose Scala didn't have in call by name parameters. How could we do it manually? What you would do, ladies and gentlemen, is pass in something which takes in nothing every time this thing is applied and this thing is called each successive time. That would prevent it from just evaluating it up front. Now we're giving it a function. Each time it needs it, it calls it with no parameter. It calls it without a
So
parameter.
that turns anything into call by name.
Yes. Yes. Except you have the inconvenience that you have to, every time you use it, you don't just say V, you have to call V with begin paren, end paren. You see what I mean?
Yeah.
So the point here is that, and this is a bit of a subtle point, but we can get the same call by name semantics, the same every time we use it, we evaluate it again, just with the syntactic displeasure of having to call it explicitly, okay? So let me see if I can belabor this point, because it may be missing for some value. Here we're going to have deferred print function v, and this is going to, let's just cut through it a little bit. This is going to be v plus v, okay? There we go. A thing of beauty, okay? Oh, sorry. Okay. This is fun. This is fun. And then we're going to have here a non-deferred, so eager print value where it just uses int. Okay. Yeah. These two are different, right? Why are they different? What's the difference between these two?
One's eager, one's deferred.
Okay, and what's the implication of that? Suppose I were to call deferred print function v here. Suppose I were to call this on print and return of 4. What will happen?
You'll print 3 times.
Thrice? I think.
8 times. Well, it'll print it. The number will be 8.
How many times will this thing be evaluated if I called this thing with it? Evaluated twice.
Okay.
Twice. 1, 2, right?
Right.
Because this print and return 4 is just prints it out twice. Okay, suppose I were to call eager print function 4. How many times will it be evaluated there? Just once. It'll call this once, get the value back, and give that value as v to this, right?
Mm-hmm.
Here, it's not calling this up front and getting the value and giving it to v. V is actually getting this whole expression, this thing to be done, right? For deferred print function 4. That's what this means. It's getting It's getting a thunk. It's getting some work to be done when it is needed. And each time it's needed, it will do that work by calling this thing, right? Here, this work to determine v is being done up front. It's called by value. It's giving it v, and then it's just using that value. Okay, now, Scott, to answer your question, here, suppose we didn't have call by name. Suppose Scala were bereft of that beautiful construct. Okay, what could we do instead? We could pass in fn get v. That is what? Well, it takes an argument and returns an int. I give me something that has me a promise. When I call it, it'll give me a v. It'll give me an int, right? And then, can I just put v plus v here?
Bracket.
Yeah, I would have to do, can I just put fn get v here? What if I did this?
No.
What would happen?
Error, open, close bracket.
Yeah, why is this nonsensical?
Because it's not a function.
Yeah, watch this. If I said this, it would be unhappy. It was like, I don't know what to do. Okay. So what do I have to do to get a value, an integer, out of fn get v? Fn get v is a function that takes nothing for parameters. It needs nothing to do its job. You just have to call it with nothing. And then it returns an int, right? So what do I have to do to get an integer from this? Call it with?
Bracket.
Yeah, call it with nothing. It says, I need nothing to do my job. You just have to call me with nothing, and I'll return an int. So this is what we'd have to do. Now, that works. And then how would we call this now? How would we call it? Deferred print. Oh, I called it.
You were it.
Okay, I didn't mean to do that. Sorry, folks. That was my bad. Okay, let's call it 5. Okay. Deferred print function 4 we defined earlier. Remember this guy here?
Yep.
This guy? Yeah. So we want to line them up. Okay. So how would I call deferred print function 5? How would I call it? Is it just like this? Would I call it like that?
I think so.
What would happen if I called it like this?
Obviously not the right thing.
Not bad. Bad things would happen. It's saying, look, you give me an integer. After all, this evaluates to an integer. This calls it right now and evaluates to an integer. And I require a what? A function. I require a function that takes nothing to do a job. So what would I have to do here?
Bracket.
Yeah, open parenthesis.
Yeah, I just have to do this. And now it's a happy camper. Look at that. Look at that. Isn't that a thing of beauty? It operates just like with print function 4. But with print function 4, I don't have the syntactic displeasure that's encountered with print function 5. Print function 5, ladies and gentlemen, I had to go both in the definition of it. I had to put in this thing. I had to call this every time I need it. I have to call it. Print function 4, by contrast, enjoys elegance and greater transparency. All I have to say is, give me a way of computing v when I need it. And then I just use it.
Now, if you pass a function that doesn't return an int,
But they do
that
the same
function
thing.
Will it throw an error?
Sorry?
If you gave deferred print function 4 a function that does not return an int,
Yeah. What would happen if I gave it something that, foo plus bar, right? Something like that. I gave it some expression. I mean, I could even give it foo. It would be unhappy. It's, I'm requiring. Here it is, and it requires an integer. I'm an unhappy camper. Yeah. Okay.
by the way, I like the fact they give you a little more information than Java does with their errors.
Yeah. Okay. So, ladies and gentlemen, what we just saw, this is a little bit subtle, but what we saw is ways of deferring computation. And the most straightforward way in functional programming to defer computation is to create something that has to be called, but with nothing. And then it will do its job. But Scala doesn't leave it there, because that way lies, if not madness, at least cancer of the begin paren end paren, right?
Hey,
Um,
list.
So it leads to this sort of need to kind of define things with greater verbosity. And when we call it, in fact, we similarly need to sort of give it, a function with extra things. Instead, Scala, by this call by name, gives us the same semantics. I mean, this is really what's secretly going on. This is what's secretly going on. When I give this, it actually creates one of these guys. And it actually accepts that in, and here it's actually calling it with no arguments. But it just is, it enjoys a level of transparency of code that's much greater from a software engineering standpoint. So call by name semantics. And that, ladies and gentlemen, is how fill works. So let's go back to our fill. Remember this?
Yeah.
This is passed as call by name. This is not immediately evaluated. If this were immediately evaluated when we called fill, it would get one double precision value and it would put it in all 10 elements.
Yeah.
But instead, this is called every time. And how does that happen? It happens, ladies and gentlemen, through call by name.
Oh, so those are dynamic parameters in logic.
Sorry?
Those are dynamic parameters
Yes.
in logic.
Yeah.
Oh, jeez.
Yeah. That's right. Okay, so ladies and gentlemen, very handy and perhaps a bit mysterious. So here we see currying going on. It takes part of its arguments up front and then later ones. And then, ladies and gentlemen, this we see call by name. This is actually evaluated on an ongoing basis, okay? But we have additional fish to fry here. So this was, so maybe what I'll do is I'll save this recording here. I'm tempted to save it and start another.